Okay, so the last part here, we're going to talk about testing your algorithms. I'll probably, just like with the R exam, I'll probably have you write some sort of simple algorithm or function and then test its efficiency. So I say algorithm or function or method simply because it could be that I ask you to write, say for homework or an exam, a method that incorporates some sort of algorithm. Okay, nothing, you know, I'm not asking you to write even um, something as simple as like what we saw in class with the secant algorithm, but something that just iterates through some procedure and something fully accessible, but that would require you to think about how to do it most efficiently. Okay, so we're going to talk about testing. So measuring that runtime, we want to understand, how our execution time might increase when the problem size also increases. So one approach is to measure that execution time for different sized problems. This is very commonly done. I like to test even for things that maybe aren't traditionally called algorithms, but computation of say critical points or something. I like to test it for different size problems. Like if I'm looking at 10-dimensional space versus 20-dimensional space, how does that change my execution time for calculation, the computation of the critical point I'm evaluating? So we can do this with the maximum segment sum algorithm. We're going to just be able to test and see how the awful approach grows more quickly than the bad approach, which in turn grows more quickly than the cool approach, okay, as we would expect. So precise runtimes may not be all that useful for describing algorithm performance because they depend on your machine. But as long as you're on the same machine, that's fine. And it's good for just doing a quick check, like, is this algorithm more efficient than the next? That's how I use it. I don't do anything more technical than that, to tell you the truth. But if you're reporting it, say for a paper, you'd need to include all kinds of information such as the operating system, your speed, and etc. But like I said, we're just going to use it to just make comparisons. And so we don't need to worry about that. And we're going to make comparisons and also characterized the algorithms as being either linear, quadratic, cubic, so forth. So if we have a linear time algorithm, it is one where the linear increase in the problem size leads to a linear increase in execution time. So what happens if we call it with, 10 million, 20 million, 30 million? Well, it should be linear. This is an example here of an algorithm. Okay, here we've written a function, which is incorporating an algorithm where we start with an initialized value for total. We just go through the range of some number n, so this is just 1 up to n, and we increase total and then return it. So it's linear. It's just gonna, the execution time is a direct linear function of the size of n. Okay, here's another one that's going to be linear. What did we change? Well, we increment total twice. So if we increase the problem size by d, the number of steps always increases by 2d. This is still considered linear time because it's still a linear function. It's just 2 times d, which is linear, right? That's the only difference. What about this one, though? Here we have an initialized value at 0. We iterate through n, we increment total, but then we iterate through n again and increment total. Is this going to be 2d or no? Make a prediction here, but I have to move on in the notes, but no, this is not going to be linear. It's no longer 2d, or it's not 3d or 4d or anything like that. This will be quadratic. So it's not going to be linear time. Increasing the problem size by fixed increments gives you a non-linear increase in execution time. So increasing from, say, 10 to 20 causes less of an impact than increasing from 20 to 30. So it's not a linear change any longer. So for this size n, the problem performs a number of steps that's actually going to be not proportional to n and hence be linear, but be proportional to n squared and hence be quadratic. Notice this happens because we have nested for loops. Nested for loops. Without the nested for loops, we would probably remain linear. This is why in the previous set of notes where we wrote the 3 approaches for solving that segment sum problem, we saw the worst case when we had multiply nested for loops. And that's because for each level of nesting, we're increasing the exponent here for the function or proportionality constant. Okay, and what are we doing here? Well, now this is like that first awful approach where we have triply nested for loops. And so this is not even going to be quadratic time, but instead it's going to be proportional to n to the cubed. So it's going to be cubic time. Okay, so you can see, I mean, it's pretty clear what's happening here. So this is why every time I teach either R or Python, I really try to drill down this idea of not using nested loops if you can at all avoid it. Think about ways to get around it, and your run time and your own personal time will be very thankful. So let's test this real quick. Test your knowledge. This algorithm is what? Well, it looks like it should be cubic, right? But what about the n's? Okay, we put in an n. That determines the value for this first highest order for loop. But then we have these other values which are not necessarily either equal to n, and certainly not equal to each other. So it's not as clear-cut as cubic. So how do we evaluate this? Or this? So here, these uppermost for loops are both n, and now this one's smaller or bigger. We don't know because we don't know n. I'm just imagining bigger for some reason. So what would these be? Would it be cubic? Or would it be not something different again? Okay, what about this one? We're going to go back and think about all this in just a moment. I just want to run through all these and get our minds going. Here we initialize sum. While n is bigger than 0, we add this constant to our sum. But each time we're dividing that constant by 2, at the very end we return sum. Okay? So what would this be? We're not iterating through all of n, are we? We're starting at some value and we're not iterating through it. In fact, it's going to be less values than if we iterated through 1 to n. Think about that. So that should give you a really strong clue with what this is. Really, really strong. We could have written a for loop here and iterated through all the values that would be included in this value, but that would be a harder way to do it. You could certainly do it that way and just set that list up and then iterate through the values of the list. But a while loop here really makes sense. Okay, now let's think about this one. Your coworker tells you she's found some way to change your algorithm so it does half as much work. Knowing that the algorithm is currently quadratic, you say, oh, that's great. That reduces our runtime to being linear, so it's going to take less time to run. Or, that's great. Our runtime stays the same, but it will finish in around half the time. Or do you say C, that doesn't do anything. Our runtime stays the same. It takes the same amount of time to run. Or D, that doesn't do anything. It does reduce our runtime to being linear, but it doesn't mean it's going to actually run faster. Okay, let's see if we can answer this within our lab this time, because this is getting at a really complex, and I don't think answering it right now is going to give you a lot of insight. Instead, observing it and thinking through why we see what we do when we go through the linear, quadratic, cubic runtime algorithms is going to help you understand the nuance here of what we're talking about. We'll continue this one in class and go through also this problem. I want you to be ready for our very last lab to work through all of these, and in fact make sure that we just focus on doing that for the whole class period in lab.